So what we have pictured here is what are affectionately known as spaghetti models. And I hope that you can appreciate why they would name these things spaghetti models. It's because it looks like wild strands of spaghetti on somebody's plate. But these are computer models, statistical models, mathematical models of the potential path of a hurricane. And they make these things to try and figure out, well, who needs to be warned ahead of time. So in particular, I kind of like this one that hooks up into the northwest corner of Alabama. So let's look at that one and see what we can figure out about it. Now, if you're forecasting hurricanes and forecasting the weather, it'd be nice to be able to tell people in this little corner of Alabama, well, when can you expect this? Now, that's not too hard of a problem if you know distance equals rate times time, but it's the distance part that's a problem. How far is this? And that's what we're going to work on, is figuring out the arc length of a curve. Now, one way you could do it, kind of a brute force approach, is to put a little bunch of dots on this. And let me get rid of the background picture now. You can just click that, shut that off. You get all these dots and say, okay, you can calculate using the distance formula, the distance between each one of these points, and then add it up, figure out the overall distance. Now, that's kind of an algebra approach. We want to take a calculus approach. And in calculus, we deal with curves, we deal with limits, we deal with integrals. We're not really fond of doing something so menial as to add up a bunch of things like that. Not that we can't, and we do, but we prefer to have something a little bit nicer. So how do we start translating this into calculus? This is actually not a bad way to begin that transition, is to divide up this arc into a bunch of points, and then see about adding up the length of the curve between each of these points. Now, let's take a look at what the book does for this. So the book takes your curve and slices it up into a bunch of different points. And then you're going to want to find the distance between these points. And then you're going to want to let those points get really, really close together. So this is adding up the distance between those points. Now the distance between those 2 points comes from the distance formula. And let me see if I can move my book enough to get the distance formula in there. That's the distance between those 2 points. This distance here, x sub I 1 minus x sub I minus 1, that's the distance between 2 adjacent points here in the x direction. You also have to deal with that in the y direction. Now for our convenience, let's call that delta x squared and delta y squared. Okay. And then we're going to kind of rearrange that a little bit. We're going to take that expression and divide out a delta x term. So let's see, where is that? Yeah, we're going to factor out a delta x term. And it's going to look like this. And then eventually, as we get around to taking limits, the limits are going to turn into something like this. And that's going to be our formula for the length of arc of a curve between 2 points, say A and B. And here it is again. So we're going to assume that we have a continuous derivative. The length of the curve then is given by this formula. Now, in my mind, a lot of what this section is a review of some of the integration techniques that we've had and some other little tricks, but it comes down to this formula. So start by writing that formula in your book or in your notes or someplace. So we're going to have L, and let's see, I can zoom out now. L equals the integral from A to B, the square root of 1 plus f prime of x squared dx. That's assuming that f prime is continuous on A to B. And that's going to be your arc length. Okay, so it's a nice little formula. And we'll take a look at it and work with some of the applications. But as kind of a starter, let's work with this example. Y equals the square root of 2 minus x squared. And we want to find the length of this curve on the interval 0 to 1. Let me see if I have some of these put up here or not. I don't think I do. No. No, I don't. All right. So we want to look at this on the interval 0 less than or equal to x less than or equal to 1. So that's going to be the limits of integration here, 0 to 1. One of the things I'm going to need, though, is the derivative here. So let's find that. I'll rewrite this as 2 minus x squared to the 1/2 power. Hopefully your powers of differentiation have not deserted you since Calc 1. You're going to have to use a chain rule. 1/2 times derivative of the outside. So it's going to be 1/2 minus 1 or minus 1/2. Am I done there? Am I done with the derivative?
To do the inside.
Times the root of the inside. Thank you. What's the root of the inside?
Negative 2x.
Beautiful. Negative 2x. And let's clean this up a little bit. This certainly will help us out. The 1/2 and the 2 are going to cancel. And this term has a negative exponent, so I'm going to bring it down into the denominator. Like this, 2 minus x squared to the 1/2 power. How about this x? Where does that go? And all this melee, what happens to the x? Is it in the numerator or in the denominator? Since it's to the positive first power, it's not going to be moved down to the denominator. I move this to the denominator to get rid of the negative. Here, this stays up in the numerator. And like I said, the 2's are canceled. Negative, I'll leave that up in the numerator as well. Okay. So it's handy to have the derivative there. That's we're going to use right here. That's our f prime. So let's set this up. This is going to be the integral from 0 to 1. The square root of 1 plus negative x over 2 minus x squared. This should be to the 1/2 power. Rats. So this is going to be to the 1/2 power, and then the whole thing squared dx. Cool.
How did you get the 0 to 1?
That's given to you by the problem.
Okay.
Yeah, they have to tell you where you want to find the arc length. So, yeah, that's a given. All right, so let's square this out, keeping in mind that that's really to the 1/2 power. So when I square a square root, essentially, or something to the 1/2 power, those two operations are going to cancel each other out. So that's going to become the integral from 0 to 1 of the square root of 1 plus negative x squared is going to be positive x squared over 2 minus x squared dx. Okay. So now what? Now this looks like a mess. Doesn't look like anything that I know how to integrate. There is one thing I can do, though, that might be helpful. Does anyone know what that might be? What's one thing I can do here?
Common denominators.
Common denominators. Perfect. Perfect. So let's write this in red to really get your attention if you were reviewing these notes. Common denominator is going to be 2 minus x squared. That's not so bad. Well, if they have common denominators, I can add the numerators. Two minus x squared plus x squared just gives me 2 over 2 minus x squared. Are we okay with that step? So I'm going to clean up the numerator a little bit. In fact, I'm going to take the square root of the numerator and the square root of the denominator. The square root of the numerator is just a square root of 2. And because the square root of 2 is a constant, I can put that out in front. So it's going to be square root of 2 times the integral between 0 and 1 dx. I'm going to squeeze up top over 2 minus x squared. This may not look familiar yet because we haven't worked with it too much, but the denominator here could start to look familiar. This becomes square root of 2 times the arc sine, or sine negative 1, that's what you like, inverse sine of x for x between 0 and 1. Actually, it's not quite x. I lied. It's x over the square root of this. X over the square root of 2. This was on one of the handouts that I sent you in advance of the last test, or in association with section 7.2 or 7.3. So if you want to check back and double check me on that. It helped if I made this a 1. So it's going to be square root of 2 times the inverse sine of 1 over the square root of 2 minus the inverse sine of 0 over the square root of 2, or just 0. This one's, a little obscure. We don't use this too often in this class. But does anyone remember what the arc sine is of 1 over root 2? I'll tell you what, a lot of you probably don't. So what if you're stuck with this and WebAssign wants an exact answer? They're like, no, don't give me, a decimal answer. I want an exact answer. And then they could do that. So here's what you could do. If you're in a pinch, you don't have a copy of the unit circle around or something like that, what I would suggest is that you put your calculator in degree mode first. So mode, come down, put it in degrees. And now I want the inverse sine. So that's right up here. To get to the inverse sine, you hit the second button and then the sine. 1 divided by the square root of 2 . And now let me address you the question of, well, why did I put this in degrees? If I put this in radians and did the exact same thing, is anyone going to recognize that? Are you going to look at that and say, oh, I know what that is? That's pi divided by 4. Not very easy. But if you put it in degrees and then say, okay, well, I can translate that to pi over 4 pretty easily. And you can double check yourself if you want to. So that's kind of a workaround if you've forgotten some of your trig values. Square root of 2 times pi over 4 minus 0 is simply square root of 2 times pi over 4 for your final answer.
Okay.
How's that one look?
Yeah,
please.
Would you accept the root 2 sine inverse of 1 over, yeah, would you accept that answer, or would you want us to simplify it?
I wouldn't be really happy about that. I mean, if this was some crazy number, I might accept it. But for numbers that are part of our special angles, you know, like pi over 4, pi over 3, pi over 6, those kind of things, I kind of expect that you can get those if you need to. I don't expect you to have them memorized, which is why I went through all this, to show you, okay, this is how you could get it if you've forgotten it.
Okay.
But WebAssign is going to want this. That's what they're going to want. So I don't think, I mean, you could try it. You get 3 attempts. You could try it and see if they'll take this. I mean, maybe they would. But if you leave it like this, you know, you're not like going to lose 10 points. You know, you might lose a point. But I probably would expect you to simplify it. So I hope that answers your question.
It did.
It's not going to be devastating if you can't simplify it to there. Like I said, it's going to be like a point. All right. Let's try some more. Was the calculator trick helpful? So give me some feedback. Was the calculator trick helpful?
Yes.
Yeah? Okay. Thank you. Okay, so this time we have x as a function of y. And again, this information has to be given to you. We want to find the length of the arc here between 1 and 4, like that. So, trying to think. Well, what we're going to need to fill in is the integral from 1 to 4 of the square root of 1 plus something squared. Now let's call this function, say, g of y. Call that function g of y. Then what I'm going to need here is g prime of y squared, and then dy. That's what I'm going to need. So let's practice doing this one, and we'll actually get a numerical answer for this one. So we'll start with g of y equals the square root of y minus 6y, which I'd probably rewrite as y to the 1/2 minus 6y. Okay. G prime of y is going to be 1/2 of y to the negative 1/2 minus 6. We could also clean that up as 1 over 2 times the square root of y minus 6. We got to take that expression and put it in here. So the hard work here was to actually calculate things and put them in the integral in the right way. So it's going to be the integral from 1 to 4 of the square root of 1 plus 1 over 2 square roots of y minus 6 squared dy. Are we okay with this much of it? Because we're going to finish this one up on our calculators. We're just going to get a decimal value. And I believe what I'm doing here is I'm mimicking what they did in your WebAssign homework on this. So let's take a look at that. Let me go to my little app here and do it here. First thing I want to do is hit Math 9 because I want to integrate from 1 up arrow to 4. Now you can type this all in with y's, but to get to the y, you'd have to hit the second button and then the number 1. That just feels like a lot of work. So what I propose is that we're going to type this in. It's just that we're going to use the variable x. The variable that you have here is a dummy variable. It doesn't matter if I use an x, a u, an r, a p, a j, a k, whatever variable you want. So for my convenience, as I type this into my graphing calculator, I'm going to type it in with an x. So the first thing I'll need is the square root. So let's do that. And you can follow along with my keystrokes on the bottom there. So second square root of 1 plus, now I need some parentheses. So left parenthesis. And I'm going to kind of keep this simple. So we'll do, well, I guess we got a choice right here. 1 over 2 times the square root of y. You're either going to need to put parentheses around that, or you're going to need to use your fancy math type functions of your graphing calculator. Which ones do you want me to use? Do you want me to use parentheses or try and do something a little bit more clean? All right, we'll use the latter approach. If you hit the alpha key, then the y equals key, the first option there is for just a nice regular old fraction. So I'll press enter. And then I can type 1 divided by, and I'll scroll down, 2 times the square root of x. And then you got to exit the square root and then exit the fraction. Minus 6, and then a right parenthesis, and then a square key. And if you're getting a little bit lost, you can see the exact keystrokes that I have down here on the bottom. Those are exactly the buttons you need to push. There's one more thing that I got to do. I got to go all the way over here to the right and tell my calculator that I'm integrating with respect to x. And bam. I'll tell you what. Why don't you tell me what answer I should be getting? What answer are you getting?
17.26.
17.26. Sounds pretty good. Anyone else? Got something different?
I got 15.95.
Whoops.
I need to see the keystrokes. I tried doing it the parenthesis way and I failed miserably like 4 times.
All right, so there's all the keystrokes from beginning to end. So as you can kind of mimic that. If you're doing it without the special little trick I used here, you need to use parentheses around both terms in the denominator. So, all right. Marissa, you got these, or can you watch the video again? Because I want to clear this out, and I'll do it again with parentheses.
Very well. I screenshotted it. Thank you.
Okay. All right. Cool. So let me clear this. Yeah, it's clear. Math 9. So again, between 1 and 4. I need to go to the right. There we go. So second square root 1 plus left parenthesis 1 divided by. Now this time I'm not using that fancy stuff. What I have to do is I have to use parentheses around the denominator. So that I don't just divide by 2 and then multiply by the square root of x. I'm dividing by this whole thing, 2, and then second square root of x. Now I got to exit this, and then a right parenthesis. Now that's just my first term here, but I still got to do the minus 6, and then a right parenthesis again, and then the squared key, and then exit out to the right, put my dx term in, and whew. So secretly I was holding my breath to make sure I got that right, and they both match, so that's good. I don't know. I think I like the first way better, but some of you might not have the capability of this extra little fraction here on your calculator. If you haven't updated your calculator to the latest operating system, you should. If you got a TI-84, you can make your calculator do these things. If you got an 83, your calculator is probably older than you are. So, okay, looking good there. Let's do a couple more to finish this thing up. Actually, several more. Let's come back to here. So a lot of what goes on in this section is, you know, a little bit of review and, you know, a couple more tricks of integrating things. So let's see. Let's do another example. This time we're going to let y equal x to the third over 3 plus 1 over 4x between 1 and 3. And I forget whose question it was, but it was an excellent one earlier. This much, again, is given to you. You want to find the length of this curve between 1 and 3. Okay. So if you want, we can call this f of x is 1/3 x to the third plus 1/4 x to the negative first. And I'm just rewriting it like this because I know I have to take the derivative. So let's do the derivative. F prime is going to be x squared minus 1/4 x to the negative second. And that's looking pretty good. Let's take a look at this quantity. Underneath, when I calculate my arc length, integral from a to b, square root of 1 plus f prime of x squared dx, I want to look at just that part. And I want to show you something kind of interesting about that part. So 1 plus f prime of x squared. I'm just going to simplify the part that's going to go underneath the radical, because there's something pretty cool and contrived that works out here. So that's going to be 1 plus this squared, x squared minus 1/4 x to the negative second squared. And that's a little bit of a pain. I'm not sure that many of us can do this in our head. So let me do that, you know, kind of off to the side. X squared minus 1/4 x to the negative second times x squared minus 1/4 x to the negative second. X to the fourth minus 1/4 minus 1/4 again. Now, why am I just getting minus 1/4? What happens to the x's?
They cancel.
Perfect, they cancel. And they cancel because when you multiply this times this, you have 2 plus negative 2. Gives me 2, or gives me 0. X to the 0 is going to be 1. So we have a minus 1/4 times 1. Now these two terms in the middle add, gives me x to the fourth minus 1/2 plus 1/16 x to the negative fourth. A lot of work here. What that turns into then is 1 plus x to the fourth minus 1/2 plus 1/16 x to the negative fourth. Man, it's just a lot of work here, right? But I see some common factors here. 1 minus 1/2. What does that give me? Come on, someone tell me. I haven't written it down yet. But 1 minus 1/2. What's 1/2? It's a positive 1/2, right? Now, if you look at these two terms here, this one and this one. Keep in mind, this one came from this squared. Squaring this gave me this. But boy, this one looks awfully like this one, doesn't it? What's the only difference?
Positive sign.
You have the positive sign here, right? Can anyone figure out what I can square to get this? What did I square to start with? I had x squared minus 1/4 x to the negative 2. I'm gonna like make that look like a real x squared. There we go. All right, well, you should take good note of this because there's a problem just like this on your web assigned homework. This is going to be x squared plus 1/4 x to the negative second squared. So that's the big trick in this. And I remember actually doing a problem like this one time and getting really, really frustrated and then finally figuring it out. I'm like, who's going to see that? I don't know. This is why I'm telling you now in lecture so that when you're at home doing this on WebAssign, you don't take my name in vain like 6 or 7 times and then hit the teacher, ask the teacher button, all right? You'll have seen this. So it's a trick that you're going to need. Are we okay with that one trick? Because that makes this whole problem work. Okay. So let's get down to finishing this up then. to find the arc length, that's going to be the integral between 1 and 3 of the square root of 1 plus, where is it? X squared minus 1/4 x to the negative second squared again dx. But we simplify that.
Mr. Barrett,
Yes.
haven't you already added the 1 in?
Well, I'm kind of going, I showed you the algebra here. What I'm doing is I'm just kind of going back to the start. So yeah.
Oh, yeah.
You're right. This simplified to x squared plus 1/4 x to the negative second squared again dx. And this is the aha moment that I wanted to get to, because this is going to simplify pretty nicely, right? Square root of x squared, those just cancel. So it's going to be the integral from 1 to 3 of x squared plus 1/4 x to the negative second dx. Awesome. And so when I find the antiderivative of that, I'll end up with 1/3 x to the cubed be a minus 1/4 x between 1 and 3. And I trust that you can finish this up from here. You'll end up with 53/6. All right, cutesy problem there. How are we looking on this one? All right. One other kind of cutesy problem for us, and then a nice real-world application, a place you can travel to in a non-COVID time, I would hope. And let's see here. So y equals ln of the secant of x, and 0 is less than or equal to x, less than or equal to pi over 6. So just a small, tiny, crazy looking little curve. We want to find its arc length between 0 and pi over 6. So let me anticipate something. I need the derivative. So see about the derivative. Remember how to differentiate the log. It's going to be 1 over u, which is secant x, times the derivative of u. The derivative of u, what's the derivative of secant? This is your turn.
Secant x tangent x.
Nice. Secant x tangent x. Thank you. And isn't that special? Secants disappear. Just leaves me with tangent of x. So cool. So y prime equals tangent of x. Let's look at 1 plus y prime squared. It's going to be 1 plus tangent squared x. So, okay. 1 plus tangent squared. Does that remind anybody of something?
That's
Secant
can
squared.
Yeah, nice. So that's secant squared. And that's what you need on this one. So to put it all into our integral, that's going to be the integral from 0 to pi over 6 of the square root of 1 plus y prime squared dx. Turns into the integral from 0 to pi over 6 of the square root of secant squared of x dx. We already did that simplification up here. And we got another problem, kind of like the last one, where you got a square root of a perfect square. That's pretty nice. It's ideal. So that just gives you the secant of x dx. And I remember when I was taking calculus that they actually proved this to me. And I'm like, God, who came up with that idea? That was really clever. But the secant of x does have an antiderivative. So this is the ln of the secant of x plus a tangent of x. And that's going to be between 0 and pi over 6. Ln of the secant of pi over 6 plus a tangent of pi over 6 minus the ln of the secant of 0 plus tangent of 0. We'll do the easy parts first. Tangent of 0 is 0. Secant of 0 is 1. So basically you're going to end up with the minus natural log of 1 from all this. And over here, secant's the reciprocal of the cosine. So you could play that same game that we played earlier with your calculator and say, all right, that's really cosine of 30 degrees is going to be square root of 2 over 3. But the secant's the reciprocal. So 2 over the square root of 3 plus 1 over the square root of 3. This is going to simplify. I'll end up with the square root of or 3 over the square root of 3. That's a big 0. I'll end up with ln of 3 over the square root of 3, which is just ln of the square root of 3. Nice. All right, there's one last problem I want to finish this one off with. If you get your calculators out, that'd be really nice. We will need them in a minute. Are we okay with that last example? All right. Let's see here. So in the link that I sent you, the link to Desmos, you can look at this link as well. Takes you to a link about the Arch of St. Louis. And in particular, in my Desmos link, I have a little set of pictures here. Here's the designer, Eero Saarinen. Not sure exactly how to pronounce that name, but he was a designer. He didn't live to see it completed. Kind of amazing how it was built. I mean, these cranes are pretty wild looking. Wow. Has anyone ever been to the Arch of St. Louis?
It's so scary.
Yeah. It's pretty cool. So the design is based on the idea that St. Louis was the gateway to the West, is where Meriwether Lewis and Clark expedition set out. So it's pretty cool. And its shape is a particularly special shape. It's called a catenary, or an inverted catenary. A catenary is the shape of a chain that would, if you just suspend a chain from 2 points on the ceiling, its shape would lay in a catenary. And it's actually a famous problem that Isaac Newton solved. Isaac Newton, for part of his working career, was warden of the Royal Mint. And he came home one day and saw a problem set to him by Johann Bernoulli to figure out the shape of a catenary. And for a long time, people thought it was a parabola, but it's not. A parabola is pretty close, but a parabola doesn't have the nice properties that a catenary would in terms of the forces that would stress out your arch of St. Louis. So they used a real catenary, not a parabola. I'm trying to think here. I think I have, let's see if we can shut these off. I think I do have that graph. So let me shut these off. So the arch of St. Louis can be modeled with this equation. Now, you might look at this and it kind of looks maybe a little bit familiar until you look very closely at one of the terms there. And one of the terms in there is not cosine, but it's something a little different. It's called the hyperbolic cosine. Sometimes just called cosh for short. And that's something we're gonna have to take use of. So let me kind of zoom in a little bit and maybe I can show you the difference between the catenary and the parabola. So here's your graph. The difference isn't really something that's really arresting. It's not gonna stop your heart. But there you go. Here's your parabola. You know, these are parabolas, but we want ours to fit right through there. So just a slight difference, not a big difference, but certainly an important difference if you're building something that's 625 feet high and 598 feet wide. Okay, let's do a little calculus and be done with this one. So let's see here, go back. So if I want to find the length of this curve from end to end, then I need to differentiate this formula and then put it in this one right here. And let's see if we can't match our calculation there with our calculation on our graphing calculator. So how would you do that? So the function is g of x equals 1250 minus cosh of x over 227, like that. Now cosh isn't something that we've dealt with in this class before. It's a hyperbolic cosine, but we can work on differentiating it, finding g prime. The derivative of 1250 is just 0. And I know we haven't seen it before, but if you had to take a guess, derivative of a hyperbolic cosine, a good guess would be, I don't know, hyperbolic sine.
Hyperbolic sine, yeah.
Yep. Now the interesting thing about hyperbolic cosine is that when you differentiate it, you get hyperbolic sine. You don't have to change the sign. It's not like the regular derivatives of sine and cosine. But there's something a little bit more. That's the derivative of the outside. Can anyone tell me the derivative of the inside? Well, think of it as 1 over 227 times x. What's the derivative of that?
0. Are you talking about the x's? Would it be 1?
Well, the whole thing.
Oh.
The whole thing. D by dx. Well, you ignore the constant, right? What's the derivative of x?
Just 1.
Just 1. So 1 times 1 over 227. So like that. So the integral that we would need to set up would be the integral from negative is negative 298 to 298. Actually, 299, sorry. Negative 299 to 299. That's coming from where the graph intersects the x-axis of the square root of 1 plus this negative hyperbolic sine of x over 227 divided by 227 squared dx. So let's see if we can make our calculators do this one for us. All right, so let me clear this out. Then I'll clear this so we have a clean slate. So math 9, negative 299, up arrow to positive 299. Right arrow takes you to the integrand. Second, and then the square root of 1 plus, and then I need a left parenthesis. I'm not going to bother to put in the negative here that's part of this, because when you square a negative, it becomes positive anyway, so it really isn't going to matter in terms of our calculation. But the big question for you is, where on earth do you find the hyperbolic sine? So let me help you out with that. You're going to find that in the catalog menu. Now, if anyone knows a faster place to find this, I don't know it, but please tell me if you find one. So to get to the catalog menu, I hit second and then catalog. And if you notice, I have to scroll down an awfully long way before I get to sine and then sine H. So there's a little shortcut though. In the upper right-hand corner, you see that letter A? That means somebody's already pressed the alpha key for you. If you wanted to jump down to the S's, you could, just by pressing the LN key. And that'll jump you all the way down to the S's. And now we can scroll down from there until we find the hyperbolic sine. Sequences, a lot of other stuff. We'll get there. Oh, some statistic stuff, which is pretty cool. Simul, here we go. There we go, hyperbolic sine. So I had to, go down quite a ways before I got that. But now I'll press the enter key. I want x divided by 227. Right parenthesis to close out the hyperbolic sine. And then to finish off the derivative, that was divided by 227. Right parenthesis, and then a squared key. Let me make sure my parentheses are balanced. Left parenthesis, right parenthesis, left parenthesis, right parenthesis. So we're looking good there. Finally, I can hit the dx term. Something's wrong. That doesn't look like the answer I was expecting. Oh, wait a minute. Wait. I forgot something with our derivative, didn't I? Yeah, I did. All right. I screwed up. I forgot when I wrote down the function here, should be this. There should be a 625 here. Now put a 625 there. So, okay. But the big thing that I wanted you to get was where to find the hyperbolic sine. You can find the hyperbolic cosine the same place. I think I can fix this one pretty quickly. If you hit the second key, then the enter key, it'll bring up your last computation. And let me squeeze in right here, hit the insert, second insert, 625. There we go. Ah, that's what I wanted. Beautiful. And if you look, that matches what we had on decimals. So, okay, that's it for arc length. Any questions or thoughts on this last one? Newton, who worked all day at the Royal Mint, finally solved this problem after spending an entire night working on it, and he communicated his solution back to Johann Bernoulli anonymously. And Bernoulli said to himself, "Ah, I recognize the lion by the print of his paw." So kind of a cool quote, but I'll leave you on that note, and we'll take a quick break.